Hello, everyone, and thanks for joining us. My name is Stuart Frost. I'm the CEO and founder of Geminos. And I want to talk to you today about what we're doing with Causal AI in action. So, show you some actual use cases with a focus on reducing unplanned downtime. Now, in general, we'll be talking about oil and gas use cases because that's where we've had a lot of traction. But the basic techniques are applicable to any industry. And you'll see that as we go forwards. And feel free at the end to ask any questions about how it might be applied to your particular situation. But the goal here really is to revolutionize business decision making. And obviously, we're very big proponents of using causal AI to solve that. So that's the main thrust here. So I want to talk initially about paths to AI-driven decisions. What are people out there looking at? That includes things like Gen AI, etc. We don't think Gen AI in particular is a good solution to this, so Causal AI is much better suited to it. We'll talk about why, etc. Also talk a little bit at high level about what causality adds to AI, and I think give you a framework for making decisions in different ways. There's a parallel here with Daniel Kahneman's work on thinking fast and slow. We think that LLMs, etc., can be used in the right context and with the right technology behind them to help you make fast decisions. But the bigger, more important decisions need a bit more thought, need a bit more planning, and that's where causal AI comes in. We'll talk a bit about the cost of unplanned downtime and draw a parallel or a contrast between predictive maintenance using traditional AI versus causal AI. We'll then roll into a discussion with Nick Phillips, who's an oil and gas consultant, very well known in the industry. We'll have a bit of a discussion with him. And then once we've got through that, we'll have a platform demonstration by Owen, talk about a few different use cases, and then we'll have Q&A at the end. So what are the different paths to making better AI-driven decisions? As I said just now, LLMs are being used or being considered to be used for this, along with agent frameworks, etc., and general things like RAG to help LLMs give you better answers. We just don't see that working in practice. We spent a lot of time with customers trying those kind of approaches, and LLMs just don't get the answer right often enough. The way I put it is that they actually hallucinate all the time. I think there's this idea that they know what they're doing and talking about 80% of the time, and then they do something different and hallucinate and get it wrong 20% of the time. That's not how the technology really works. They don't understand the world at all. So they really hallucinate all the time. It's just that they happen to be close enough to being right about 80% of the time. And the rest of the 20% of the time, they just get it wrong. That's not good enough when you're making real decisions that have business impact and potentially safety impact. Lives might be at risk. So clearly, that's not going to be good enough. And agents don't help you there, really. I mean, all they're fundamentally doing is using LLMs at various stages and breaking down what might be a big decision into smaller steps. But if you're still only getting it right 80% of the time, once you've gone through a few steps, it's generally pretty wrong. So agent frameworks, etc., are good for demos and fairly simple things. Once it gets to real complex decisions, it's just, in my humble opinion, a pretty dead-end technology. We use it in different ways where we can use it as an aid in various ways, but in terms of making critical decisions, it's just not going to get there. And scaling isn't going to solve that problem. I think the scaling hypothesis is fundamentally broken, and we need a different way of addressing these kinds of challenges. And my firm belief is that causal AI is a big part of that. And as you'll see as we go forward in the slides, it's a really effective technology for really dealing with these kind of complex decisions. And in my career, I've been looking at helping my customers in industry make these kind of decisions now for decades. And this collection of technologies now that we're putting together is a massive step in the right direction. It really is a big breakthrough. And when combined with technologies like the causal knowledge graph that we've discussed in other presentations, I think this is a great foundation for solving these kind of problems. So what does causality add to AI? It's fundamentally about helping me understand why is something happening that I just don't really do or get out of correlational AI, traditional AI. There is no why about it. But going on from that, it's also what can I do? How can I intervene to do something different and get a different outcome? Um, and then counterfactuals. What would have happened if I did something different, if I had done something different? And at the end of the day, that is the core of making better decisions. It's no good just telling me what might happen perhaps in the next few days. Tell me why. Tell me what can I do to fix it. And that's where causal AI really changes the game. This is something that has been around for several years now. It really came out of research by Jadair Pearl at UCLA. It's got a great scientific background. There is a math behind this, an AI engine behind this that Pearl designed and developed. And it's being taught in a lot of the top schools now as part of data science and computer science curriculum. So this is something that is starting to get out there in industry more and more. And we feel we're right at the forefront of helping customers to use this to solve real world problems. Let me just go back to this decisions fast and slow concept. So the way we look at this is similar to Daniel Kahneman's thinking fast and slow. So LLMs plus agents with the right foundation of a causal knowledge graph can help you to answer general questions, obviously language driven, not really data driven. There's still a lack of precision, so we've got to be careful not to count on it too much. We have, I think, greatly reduced and shown that we can greatly reduce bias and hallucinations, but still, it's a factor. So they're not really good for key decisions, but can be quite good for knowledge sharing if they're used in the right way. One of the things that we're doing is using LLMs and agents to really help you build that causal knowledge graph and really provide a foundation for sharing knowledge across the organization in a structured way. Knowledge graphs have been talked about for decades. They've always been a challenge to build. I think now what we have is the tools available driven by LLMs and agents to really help us solve that problem. And that can help us when we do causal AI to really address specific decisions that need to be data-driven and precise, no hallucinations, etc. It's not necessary to build a whole causal knowledge graph. I want to be clear on that. You can use the tools without it, as you'll see in the demonstration a little bit later. But we are finding that it gives people a faster start and an ability to spread the technology across an organization a bit quicker. But it can be done project by project. We're not talking about boiling the ocean and building things for the entire enterprise. But that combination, I think, is starting to be really powerful, and our customers are starting to see real value from it. Let's talk a bit about the predictive maintenance challenge, traditional versus causal AI. With traditional AI, correlational based, we can maybe get some predictions as to when failures may occur. But that's only if that pattern's been seen before. And also, it is just based on correlations. So it may not be truly causal. We might not be getting a very accurate picture. And certainly traditional AI does not explain why those failures are going to happen. And they doesn't recommend what to do about it. Causal AI also adds to all of that the fact that we can identify root causes, because it truly is based on historical causation and there's that mathematical model behind it. So we're really able to get actionable insights out of causal AI that we just can't get from traditional approaches. So it really is a big sea change in the way we can address these kind of challenges. Okay, what I'm going to do now is introduce Nick Phillips to the conversation. Hi there, Nick. Thanks for joining us today. How are you, Nick?
Yeah, very good, thank you. My apologies, there may be a slight delay in the
So
audio on this. Are you still getting that?
it's a very, very slight delay, but no problem. Don't worry about it. That's good.
Okay.
Yeah. So maybe you could just spend a few seconds introducing yourself, Nick.
Sure, yeah. My name is Nick Phillips. I've been associated with the oil and gas industry for best part of 40 years now. Um, Mostly in the upstream, midstream sectors, but latterly also in the downstream sectors. And that's all the way from operations management through strategic planning and also on the technology and innovation side latterly. So a broad knowledge globally, based in Houston, Texas for many years, working with some of the largest multinational service companies in the industry.
Very good. Well, let me ask you a few questions and we'll just have a general discussion. Just spend maybe
Hmm.
10, 15 minutes and then we'll switch to the demo. So in your view,
Sure.
what are the biggest cost drivers in the oil and gas sector? And specifically, how big a role does unplanned downtime play?
Hmm. Yeah. I mean, you take it back to the very start of an operation. You start with exploration costs, typically very high. Then you come on to drilling costs. And then once you've done that, you've got your asset in place. Then you've got the operating costs of that facility. And then on top of that, you've got overlay regulatory costs, political costs, all of these. So these are all major cost drivers within an operating company. Um, and they all play a major factor in the overall financial burden of that company. But if you look at that, and coming back onto the operation side of it, once an asset's operating, once it's producing, then that is the revenue source for that company. So you talk about unplanned downtime, or in fact any downtime, but certainly unplanned, that has a major implication and impact on the finances of the company, on the plans for that company. And so you can look at in today's markets, I think this is sort of an average number, there are around 25, 30 unplanned shutdowns for any company in a year. And these have implications on the order of, let's say, 30 or $40 million per annum as a consequence of these unplanned shutdowns. So, in terms of manageability, once an asset's running, an unplanned shutdown has a major implication on the financial health of any operating organization.
Yeah, absolutely. I was fairly surprised, I must admit, when I engaged with a few customers on this and to see the impact, not just of, okay, something's broken, we need to fix it, but you've got to take into account the cool down time often, right? These are typically things running at very high temperature, very high pressure. You've got to effectively bring it down, might even take a few days for that to happen. And then you've got to heat it back up
Yeah,
again, put it under pressure again. And often that
yeah,
cycle can cause future problems as well if you try to do it too quickly. So often an unplanned downtime can be weeks. It's not just, a matter of, hey, switch a
absolutely.
component in, right? Yeah. And the
Yeah,
lost production from that can be millions of dollars each time.
yeah. And one of a key factor underlying this is, we're developing oil and producing gas in more and more complex environments. Assets are aging. Um, and so a consequence of that, complexity is increasing year over year over year. Now, as you increase complexity, the number of known variables starts to reduce. So our abilities to effectively manage on or reduce unplanned downtimes is becoming more and more difficult. And hence, there's more and more unplanned events, which have, as we just discussed, those financial implications. Not only financial, but if there are wider implications on environment, for example, then there's these potential effects on an organization.
Yeah, absolutely. And, one of the things that we're seeing is that traditional AI isn't all that effective often in these kind of environments because You don't necessarily see
Mm,
all that many events, but when they happen, they're really bad. And they can be a little bit different
yeah,
as well. And unless you really understand the causal factors behind all those and have a real causal model of what's going on in that equipment, you just don't get the help you need to make better decisions. So this is, I think, why we've had such great success in this particular area of operation, not just in oil and gas, but other areas as well. But it's a big deal here, right? Because it can be literally millions, if not tens of millions of dollars, and it is quite hard to predict using traditional techniques. Um, so, that's kind of goes into the next question, really. But, how have you seen in the past customers going about this? And where do you feel the
yeah,
real gaps are,
yeah. I mean, recognizing any abnormal behavior is critical. Um, and looking at sort of methods that companies have employed and continue to employ today, you've got predictive maintenance, anticipate equipment failure, which allows for more scheduled maintenance repairs before shutdown occurs. You've got early warning systems, developing systems to detect potential issues and identify the causes of those, maybe. And certainly process optimization plays a lot of this, which is, where do the inefficiencies lay in my operation? And it all forms part of a continuous improvement cycle. And then what can be done to minimize the risk of failure going forward? And that's obviously that minimization leads to any unplanned shutdown. And a big issue is around this, obviously, is not managing this effectively. There's potential implication on safety, and any operating company, safety is the number one priority. So really, outside of managing these events through predictive maintenance, early warning, etc., we're always coming back down to our key drivers of safety and environmental.
Yeah.
Um,
Yeah, absolutely. We see that as a common path. People might start with a predictive maintenance or even prescriptive maintenance application. Effectively, that's where we end up. And then move on fairly quickly to, oh, now we're seeing this technology work in practice. Can we apply it to
mhm.
health and safety and ESG metrics and so on? And the answer, of course, is yes. The
Yeah,
Causal AI is a very general technology that can be applied to all different kinds of use cases, different sectors, etc. And what we see is really a lot of these decisions are chained together. So to your point there, you might start to think about predictive maintenance and, as you get more uptime, does that put more stress on the organization? Or,
mhm.
you're getting perhaps more throughput. Well, what happens to other components that might start to wear and so on. So a lot of these decisions are chained in the end, and one does lead to another. And any interventions I might
Yeah,
make in one area might impact all kinds of areas, right? I might even reduce my production overall in order to lengthen the life of a component. Is that a good thing or a
yeah,
bad thing?
yeah,
Balance, right? Um, so yeah, what we see is that kind of almost viral progression through an organization as they start to see the value and see how these things are related. It really gives them for the
yeah,
first time the ability with the operations people to see the real impact of their decisions on other areas.
yeah, yeah, absolutely. Mhm.
Very cool. Well, let's move into the demo section and we'll have a Q&A session at the end of this anyway. So there'll be an opportunity for the audience to ask more questions and I'm sure you'll be able to give some insights on some of those too. So I'll share my screen again.
The example we're going to be looking at today is how we've applied causal AI to make better decisions around damage that causes unplanned downtime to a heavy industrial asset. Despite this particular example having an oil and gas focus, this is broadly applicable to a wide variety of industrial use cases. Fluid catalytic cracking units, or FCCs for short, are used in many oil refineries across the world. They're used to convert heavy hydrocarbons into lighter, more valuable products such as gasoline, diesel, and kerosene. They provide companies with a greater deal of flexibility to meet changing market demands for petroleum products, and they also have a higher yield compared to other refining processes, so it's a very important piece of equipment. The catalyst used in these FCCs is usually a very fine powder such as aluminosilicate, which takes on fluid-like properties inside the asset. Remember this for later. Just to give a quick overview of the process at a high level, let's refer to the diagram on the left. Catalyst and feedstock, which is usually vacuum gas oil, known as VGO, enter at the bottom of the riser, where they flow upwards and react together. Once they reach the top of the riser, cyclones in the stripper will separate the spent catalyst from the products, which then flow to the next stage of the refinement process. The spent catalyst is regenerated by combusting the coke that has formed on its surface in the regenerator. The regenerated catalyst then flows back to the bottom of the riser, and the process continues from there. Let's define the specific problem that we're trying to address here. The process runs continuously, so unplanned downtime is clearly costly, as it so often is with industrial assets. Over the last 7 or 8 years, a company operating one of these FCCs has been trying to reduce unplanned downtime by mitigating erosion and corrosion, which are two very common damage mechanisms across many different assets. Once damage reaches a certain point, the likelihood of a failure leading to downtime becomes very high. Different designs of both the catalyst and the asset itself have been trialed, but due to the complex nature of the process, they've struggled to assess whether those previous trials have been a success or not. And again, it's more than just understanding why the damage and failures happen. We want to know what decisions we can make to mitigate or prevent them in the future. Now that we've introduced our problem, let's start building out the solution. The first thing we often do is build a causal model to represent the system we're interested in. Starting with subject matter expertise, whether that's interacting with Causeway Copilot, reading passages from manuals, or in the form of an interview with a subject matter expert, we can extract causal variables, those words that are highlighted in black in this paragraph here, along with causal relationships, those words that are highlighted in blue. This information can then be represented in the form of a model, with arrows between variables to represent causal relationships. We can then assemble a series of these into a first draft of our causal model, which forms a set of testable assumptions that we can evaluate and iterate on after doing some initial analysis. Let's start by recreating an example we just looked at inside Causeway Studio. We'll do this by dragging and dropping a few nodes onto the canvas, giving them names, and connecting them together to define those same causal relationships that we saw just now. If we're ever unsure and want some help getting started with a causal model, we can always use the Copilot directly inside Causeway to recommend some causal relationships based on a research question. We can then add those causal relationships directly to the canvas. Once we've spent some time building out the causal model, we'll end up with something that looks like this. You'll now see that the model has our key outcome, FCC reactor damage, highlighted in yellow on the far right, which every other variable is either directly or indirectly related to. You'll notice that we do have another variable further to the right than FCC damage, which is output yield. We've used output yield as a proxy outcome due to the difficulty of regularly inspecting the reactor, as we mentioned before. One of the benefits of creating causal models in a visual interface like this is being able to easily identify potential proxies as and when they are required. On the left of the model, you might recognize the treatment variable that we mentioned earlier, catalyst design, which has been split into 2 separate nodes in the model, one for particle size and one for density. Similarly, the vessel characteristics at the top reference the material used as well as the thickness, which will affect both damage mechanisms. We've also included some other key causal variables related to the operating conditions of the FCC, such as temperatures, pressures, and flows. Another one worth highlighting is the feedstock composition. This represents the sulfur content of the feedstock, which can exhibit a great deal of variance due to variations in the type and quality of crude oil available to the company at any given time. This causal model directly corresponds to the FCC dataset, which we can take a quick look at. This is no coincidence, as once we built the causal model, we then fetched the relevant data from historical sensor recordings. These readings were taken multiple times per day over the course of several years, so we have a decent amount of data to analyze here. You can also see the points at which changes were made to catalyst and vessel design. Now that we have both the causal model and a dataset, we can run some analysis inside Causeway Studio. We can start by building a functional causal model, which will help us to quantify the various causal relationships at play in our model. This works by estimating an underlying function for each variable in the model in terms of its parents. To explain a bit further, if we focus on output yield in our model, it has 5 parents, highlighted here. If we take a closer look at output yield, we can see a function has been estimated for this variable in terms of its 5 parents, each with its own coefficient. We can visualize the coefficients across the entire model, which gives us a better idea of the relative strength between each of our causal variables. We can also see the direction of the relationship. The green lines indicate a positive relationship. For example, when catalyst velocity increases, erosion increases, which matches our intuition. The red lines in our model indicate negative relationships, such as FCC damage to output yield. This again matches our intuition that when damage to the asset increases, the efficiency of the process will decrease and the yield of the products will decrease as well. Now that our functional causal model has been built, we can go a step further and do some intervention analysis. Interventions allow us to explore hypothetical what-if scenarios, which helps us to make better decisions towards our outcome. First, we can select a variable to intervene on. In this case, we'll choose catalyst particle size. We can then choose what type of intervention we want to make. A shift intervention is a relative change to the original data. So if we were to make an intervention of -10 micrometers, since this is the catalyst size, every value in our original data would be reduced by 10, and we could then simulate the impact this would have on our outcome. Atomic interventions are where we set the variable to a single value, so every value in our original data would change to be the same, which would have a different impact on our outcome. Let's run an atomic intervention of 100 on catalyst particle size and see the results. We can now see a graph for output yield with 2 distinct distributions. The green distribution is the pre-intervention data, which is our original dataset. In light purple, we have the post-intervention distribution, which shows what our output yield data would look like if we had made this change to catalyst particle size. We can also make 2 key observations about the differences between these distributions. The first one is that post-intervention distribution is further to the right, which means that this intervention has achieved a general increase in output yield. Secondly, the shape of the distributions are fundamentally different. The post-intervention distribution has far lower variance, meaning this intervention would also achieve a much more consistent output yield. These observations are both backed up by the summary statistics underneath the graph.
Everything that we've just created inside Causeway Studio can then be deployed as a decision application, like this causal dashboard that we've created for the FCC unit. The graph in the top right shows the damage to the FCC up to the current day, along with the projected remaining lifespan of the asset. On the left, there are a set of sliders which correspond to the causal variables we mapped out in our causal model. When we adjust one of these sliders and make a change to a variable, this has an impact on the remaining lifespan of the asset, as well as the overall output yield. A set of changes can be evaluated simultaneously to find the best outcome given the current operating conditions. If something outside of our control, such as feedstock composition changes, we can also evaluate the best course of action to mitigate the impact on our outcome. These insights are driven directly by the functions and interventions that we previously produced inside Causeway Studio, making it easier to understand and explain the results to key stakeholders.
Finally, let's take a quick look at a couple of other use cases where Geminos has applied causal AI to real business problems and helped companies make better operational decisions. Flow assurance, a field focused on ensuring smooth and efficient fluid transport in oil and gas production, plays a critical role in minimizing unplanned downtime. Oil wells very commonly suffer from buildup of deposits, such as asphaltenes, which can lead to devastating production losses, with some extreme cases leading to costs in excess of $70 million. Causal AI can help by identifying the optimal time between soaks, as well as the soaking time itself, for solvents such as xylene, which are used to remove these deposits. This approach also makes it easy to evaluate the introduction of different additives, which is another common solution to this problem. Optimizing the use of xylene also has large ESG benefits, on top of the significant cost savings of reducing downtime. Another use case that we wanted to quickly mention was the maintenance of industrial gas turbines. They play a vital role in power generation and mechanical drive applications. Downtime of these turbines can be particularly costly, as they propel so many other industrial processes. There are a few key challenges around understanding causes of failure for gas turbines. Most turbines have multiple complex failure modes, plenty of which will have common causes across them, making it difficult to determine the true cause of a single failure. It can also be difficult to determine the true cost of a failure, since failures to these turbines can have meaningful impact to processes far down the production line. Causal AI is designed to specifically address these key problems. The fundamental approach of causal modeling makes it far easier to diagnose the root cause of a failure, and it's also possible to chain multiple causal models together, making it so that companies can evaluate the impact of a failure to a single piece of equipment on the entire production line. To summarize, Causal AI has demonstrated clear value in reducing unplanned downtime for industrial use cases. This represents a significant opportunity for cost savings across many different industries, not just oil and gas. The benefits are definitely not limited to just maintenance problems as well. So if you're interested in learning about other use cases, feel free to get in touch. Thanks for watching.
Okay, so nice demo taking us through a few different use cases, and hopefully you can see how it can be applied to different industries as well. At this point, we'll turn it over to Steve to ask any questions.
So there's a few questions that have come through. I've answered a few of them in sort of short form on the chat window, but one question that came through from Drew Ellis was around the size of the data sets that we use to apply to Causal AI. The specific question was, what are the data requirements for Causal AI? We have limited data, not massive big data with years of operational information.
Yeah, that's a great question, actually. So one of the things we found is that we are able to build these models on a relatively small amount of data. And it's interesting. So one of the problems with traditional AI is that you do need to really put whatever, massive amounts of data in there in the hope that you can find sufficient correlations that are actually useful. We're turning that on its head a bit. We're really getting a deep causal understanding of the process, which variables are actually important, and then we're able to use the data for those variables to really understand the, as Owen showed in the demo there, the kind of true causal relationships and the strength of those causal relationships. So the training process, if you like, is totally different. You really just need enough data to understand the distribution of each causal variable and enough to kind of fit the curve, if you like. Obviously, there are limits to that, right? You need sufficient data to get a decent fit, but in most cases, it's orders of magnitude less in certain cases anyway than we've seen with traditional AI. And I've deployed both. Previous startups of mine tried to use traditional AI to do these kinds of things, and absolutely massive problem. We needed tons of data. With this approach, it's quite different, much better.
On projects that we've worked on, I think the smallest data set that we ever used, and it clearly needs to be very good data when you're dealing with these numbers, but I think something like 20 records. I mean, but you're normally on a project dealing with hundreds or thousands. It doesn't need to be tens of thousands or millions.
Yeah, absolutely. I mean, 20 would be an extremely
Yeah, that was
yeah.
an outlier.
Yeah, to say the least. But yeah, it's not like millions of rows, and the main thing is really that you've got access to both the data and subject matter expertise, right? You've got to combine those two to get a good picture of what is really going on and what is truly causal. Often people spend a lot of time cleaning up data, and the end result isn't that helpful because it's not actually causal. So just cutting that out can help.
Great. We had another question from Rishabh Sukla, who's currently he's an MBA graduate at Boston University, worked with Honeywell for 6 years in oil and gas asset performance monitoring. Looks like he's a great advocate of Causal AI for equipment monitoring. So the question that Rishabh had was, for vibration monitoring in multi-stage compressors, be it centrifugal or reciprocating, does the product offer customized configuration for stage-wise monitoring? So a fault symptom model or calculation model for users to understand what's inside the black box of AI and build trust and transparency. And he's highlighting that this was a major concern with a few clients of Saudi Aramco and Reliance in refineries in his previous life.
Yeah, absolutely. Well, it makes sense, doesn't it? And one of the big advantages, of course, with the causal model is that it is transparent. People, business users, subject matter experts can look at those high-level models. They don't necessarily have to understand how the functions are all created and the meaning of the math by any means. But the basic diagrams that show one variable affecting another one, it's common sense, right? It's how humans work, and certainly in a business context, people understand that. So I think you get a massive benefit right from the get-go of transparency, whereas traditional models, being black boxes by their very nature, you just don't really know how it's thinking about those different characteristics, whether it be vibration or different pressures or whatever it is inside the equipment, right? So I think absolutely. I mean, and hi, Rishab. I think we've spoken in the past. So yeah, it's a massive benefit that we didn't go into a great deal of detail on the presentation, but thanks for bringing that out.
Great. So another one from Michael Salas is, and it's related to Drew's previous question really, is when you have a smaller data set, do you have issues with underfitting?
Well, of course, it's always a risk, right? But the nice thing with this is that you do have a lot of tools available that indicate whether you've got problems in the model. And one of the things that we always look for is, do I have a missing variable, unobserved variable, something that I haven't got a sensor reading for, that might actually be causal? And what tends to happen then in the modeling is that you end up with noise, which is effectively kind of it can be poor fitting. It's, might be an actual missing variable, not just necessarily not enough data for a given variable. And what you then do is go through an iterative cycle of saying, okay, what might be missing? Let's ask the subject matter experts, what's going on here? And can we simulate the data for that variable? And can we make a sensible simulation based on subject matter expertise and the chemistry and physics of what's actually happening? And we can go test that and see if the noise is reduced. And we say, okay, based on that, is it worth investing in an additional sensor or whatever? And we can apply the same techniques to a certain extent to limited data sets, right? If I'm finding that I've got indications in the model and the math that I am seeing some underfitting or for that matter, overfitting, what can I do about it? How do I go about testing that in terms of leveraging subject matter expertise and maybe simulation engines even, right? What is really going on? So that gives us really far more insight into what might be happening than with traditional AI. And we're finding that to be very, very powerful. And it's a key part of how you build these models to be effective and help you make good decisions at the end of the day. So yeah, it's, you know, there are limitations, of course, if you simply don't have enough data, or the data is very, you know, random, not easy to fit to. You can have problems with it, but we generally don't find that's a major challenge, I would say.
Michael also asked this question that does come up now and again, is how do we reduce bias within these models?
So bias, there are specific techniques as you go through the modeling approach and the process to eliminate sources of bias. This is kind of a big part of what Judea Pearl talks about, and you know, if you look at online classes on causal modeling. So what you're doing really is looking for what we call backdoor paths. So through that causal model, there may be a variable that in effect kind of, you know, affects the causal relationships that you're actually interested in. I'm trying to keep it at a high level, but so what you're doing is looking for those variables and blocking them. And there are specific ways of blocking those backdoor paths. And that is fundamentally removing sources of bias. It's a very powerful aspect of causal AI that in some ways it kind of happens as you go. What we found, I think in some of the books, it's one of those topics that a lot of people talk about. And then we found that in practice, you don't have to worry too much, because if you do the process right and you build the models accurately, it kind of falls out as you go. So you don't have to put too much effort in to that stage of it. But the end result is a model that really has these sources of bias eliminated, or at least mitigated to a great extent.
Excellent. We've got a question from Jeff Hockman. He's asking, could you please provide some other examples that are maybe not industrial in nature, from service industry or something like hospital efficiency or other similar industries? How is this applicable in different sectors?
Yeah, we've not done much in healthcare. Causal AI or causality and causal inference is certainly applied there in an academic sense. But our focus is generally more on industrial and manufacturing. So I'll generally stay there, but to give you a couple of different things. One of the things is inventory management. All too often traditional systems like SAP and so on, they take what I would view as a relatively short-term micro view of planning inventory. And that can get overwhelmed by macro issues like extreme seasonality, etc. With one of our customers, we were able to show savings of over $50 million a year by taking that more macro view, really looking back through the whole supply chain to see, were they overloading suppliers? Was that causing more challenges, more premium freight, that kind of thing, and really just overwhelming the traditional parameter settings within SAP? And the outcome was absolutely yes. In a completely different industrial setting, we're working with a customer right now on semiconductor production, where the milling machines are, the wear on them is impacted by various factors. So that's another area that causal AI is a great fit for. But we've generally stayed away from financial services, healthcare, etc. And that's largely just as a startup. You know, we have to focus. We want to go deep with our customers, really understand their problems, and that's what we've chosen to focus on.
Great. We have a question from Alejandro Garcia. Recognize that name. Hello, Alejandro. When feeding lots of data, has Causeway discovered correlations that weren't identified by experts? Any cool discoveries? And how do experts react? Great question.
Yeah, it's an interesting one. So certainly when you get into analyzing complex sets of time series data, the technologies that we've built into the platform can identify patterns within those the diverse time series data sets that would be impossible for a human to tease out, right? because what it's doing is looking at what could be, across, let's say, a couple of hundred different sensor readings over several years, maybe even down to a millisecond timing or something. The sheer quantity of data is overwhelming for humans to think about and get their heads around. So I think this is a great use of that kind of technology where it's looking for recurring patterns within those time series data sets, understanding that the causal impact of a change in one variable comes later in the other variable, right? There is a time difference, which again is quite hard sometimes for humans to think about, especially because some of those time differences could be milliseconds, some could be months or years, right? So you've got to think about it in all those different ways, which is just impossible. And it's relatively common when we're applying that kind of technology to show insights that just weren't known in the organization at all. Yeah, absolutely. How
I guess we. Sorry, go on.
Yeah, how do they react? I think in most cases they're fascinated by the technology insights, right? And I think especially because, let's face it, most people have started using LLMs to think about different aspects in all kinds of areas of their life. And this is the first time that an AI has really been applied to very complex data streams like this. So when you're showing those kind of insights, it's like light bulbs go on, right? They go, oh, well, okay, that's totally different even to the Gen AI experiences I've had. And it's giving me insights into what is really going on in this piece of equipment in a way that, yeah, it's overwhelming. There's no way I would have got there. So we don't get, frankly, significant pushback, even from the operations people who might have, had 10, 30, in some cases, 30 years of experience of running a particular piece of equipment. But they're usually surprisingly open-minded about this, and really
excited even.
Yeah, they're excited and they dive in, right? And they're like, oh, wow, okay, so if that's changing, and then it creates this ripple effect. I hadn't thought about that. Okay, explain that to me better. Let's get some more data for this. What might you have missed? Okay, let's go around this loop again. So yeah, that part of the excitement is great for us as well, right? As partners to our customers in driving these impacts. Yeah, we don't see a lot of pushback in that respect.
And I guess it highlights the limit of the possibilities of just trial and error, trying one intervention at a time. And we've seen that on a few projects where they've actually achieved some amazing results, but they've reached the limit of what they can do by doing this, by trial and error, using subject matter expertise. Like you said, the excitement of being able to put all of these variables together and look at several interventions, sometimes tens or hundreds at the same time in combination, to look at the output there, that's quite exciting. It's not possible with a human.
And I think also going back to the comment when I was having the conversation with Nick about the connectedness of and the ripple effect of these decisions, right? All too often people are in their silos. They don't really have visibility of, okay, if I make a decision here to reduce the flow, what does it do to the next stage of production? What does it do to overall profitability? What might the health and safety implications be of that? And for the first time, we can start to actually give them that. It's very powerful.
Great. We've got a question from Carla Lowe. I think I've pronounced that. Forgive me if I haven't pronounced your surname correctly. So Carla's question was, during your previous seminar, you talked about the use of knowledge graphs in the causal process. Do knowledge graphs form part of the Causeway platform? Does it form part of the first step in building the causal model, or are the knowledge graphs used elsewhere in the causal process?
That was a great question. So all of the above, really. So the idea in building what I've called the causal knowledge graph is really for it to be the hub of all an organization's AI initiatives. So it's not just something that can be used to build causal AI specific problems or projects. It can be used to make your LLM initiatives work better. It can be used, therefore, to make your agentic initiatives work better. Even your traditional ML and DL projects would benefit from it. So the idea really is for the first time, we can build an enterprise-wide knowledge graph pretty quickly, pretty accurately, keep it alive as it grows and as the organization changes without it being this massive boil the ocean, never ending, we never get there project that knowledge graphs have been in the past. And what we've done is added the causal aspects to that so that you can start to understand, what is really going on in a more dynamic sense. So traditional knowledge graphs are, in my view, quite static, right? Entities, relationships, etc. With the causal information, it's okay, if something changes, what impact does it have? What is the process that we're going through here? Um, what might break if I do something, right? So that's foundational then to the kind of causal AI models that we're building to address specific pieces of equipment, specific problems at a specific point in time. And we can then feed back the learnings from that into the causal knowledge graph. So it's really pervasive. Um, it's not mandatory to go build a causal knowledge graph in order to use the causal AI tools by any means. Owen did do a quick demo there of just showing the Copilot. That can use a public LLM if you wish. You don't have to build a knowledge graph to underpin that. If you do, you'll get much better answers, don't get me wrong, but you don't have to. So yeah, I mean, you can buy the basic studio modeling tool, use that, use a public LLM if you want. But if you want to do something on a more enterprise scale, we'd strongly recommend going down the path of building a causal knowledge graph. And as I say, really using that as the foundation for your AI initiatives going forwards.
Great. We've got one final question from Michael Salas again. So he's saying, if I'm looking at just vibration data and trying to be predictive, I'm only looking at one source. However, if I look at vibration, temperature, pressure, etc., now I have a much better picture of the system as a whole. This seems it would help with looking at causal factors. Would this be causal AI or traditional AI?
Well, my humble opinion is that causal AI is just better, right? So it's not like an either or. What I would say is once you've kind of gone to causal AI, you don't go back, right? The light will go on and you'll just start getting better understanding of your systems and better results. And largely because you can say, well, why is that changing? Why is that likely to happen? And what do I do about it? And once you can do that, why would you ever go back? So I think that's part of it, right? And the more variables that can, have a causal impact that you can throw at the system, the better, right? From that point of view, the richer the results you'll get and the more insights you'll get. Um, and you throw in all the other benefits of, we can get away with smaller data sets. We can remove bias. It is more transparent. Collectively, I you won't go back to traditional AI, given all of that.
And I guess as well, just to add to that, if you've got lots of variables that give you a better picture of what's going on, you're ultimately looking for correlations in that data and making an assumption that they might be causative, causal. That one thing is affecting another because you can see a correlation between two data sets or three data sets or whatever. So with causal AI, you can actually back up those assumptions or refute them by doing the causal analysis on that data. We can truly understand whether they are related to each other or they just happen to be coincidental correlations.
And that's the fundamental issue, right? It's that, okay, so I use traditional AI, I find some correlations. Are they useful or not? We don't know. And until we, run it for a while and see if it works over time, we'll never know. And there's no real transparency into why that might be the case or not. Causal AI right up front forces us to address those critical issues. And that's why it's fundamentally better. It just is. So yeah, I mean, for me, having gone through all the cycles of the various AI technologies over now a 30-odd year career in complex data analytics, etc. This is just like, oh my God, I wish I knew this 30 years ago, right? It would save so much time, energy, money, gray hairs, you know. So yeah, this is a big breakthrough, and I can very confidently say it's the right way to go about it.
Great. Well, that pretty much wraps up the Q&A. I think we've covered most of the questions. Great session. Thank you, Stuart. Thank you, Nick. Really interesting. We'll make sure that the recording of the webinar is available afterwards. We'll send a link probably tomorrow, and look forward to continuing the conversation. We'd love to dive into your own specific use cases and questions that you've got to explore applicability of causal AI in your particular problem domain. As we said earlier, we've just focused on oil, gas, energy today, but it is applicable to other sectors, and we've got particular sort of experience working in heavy industry, agriculture, and those sorts of sectors. So thank you very much, everybody. Speak soon.
Thank you.